Okay, we're going to do a little more with derivatives and delve a little deeper. This time we're going to look at derivatives and tangent lines. I'm not expecting that you have any familiarity with tangent lines, although you may have seen in your life a circle that is attached or is intersected by a line at just one point. Let me see if I can draw such a thing best I can. That should have been connected. I'll put a dot here just to indicate a point of tangency. Now what you might know about the circle or the line touching the circle is that it touches it in just one spot, and you might be tempted to say, well, any line that touches a graph in just one spot is a tangent line, but that's not necessarily true. That's only true for a circle and maybe one or two other things. To define a tangent line, you actually need calculus to do it. There's no other definition other than calculus definition for a tangent line. Let me show you what I'm talking about. You may see various graphs. Let's say we have something like a parabola, and you'll see a line that touches the parabola at just one point, and chances are that is indeed a tangent line if it touches just at one point. However, if you have some sort of a cubic and you go and compute a tangent line, say here, then when you draw your tangent line that's supposed to intersect just at one point, you'll see that it might strike at another spot. So the definition where it connects just or touches the graph at just one point won't do. What we need is something a little more. So what we're going to do is we're going to look at a sequence maybe, or a limit, where I have some sort of a graph. Let me make it bowed enough so that my example will make sense. Put arrows at the ends of these. And let me pick myself a number a on the x-axis so that the y value can be called f of a. In fact, this point right here is a comma f of a. Let me change that X looking thing to an A. Now pick any point somewhere not there. Let me go up here. I'll just call this some point X comma F of X, just like I had there. Now what we're going to start doing is looking at lines that connect those 2 points. And so I'm going to draw a line that, if I can, my lines don't look that good because my ruler is just paper. But let me go ahead and draw one if I can. It goes through those points. And I can't even fix it if I wanted to. I don't know if I can or not. Let's see if I can fix it. To include that spot. I have a feeling it's not going to be good. Nope. Well, you get the idea. Anyways, this line that connects these, I'm interested in the slope of this line. So this line is called a secant line. And the slope of that secant line is written as m sub sec. So m for slope, because m is always used as slope. And if you'll remember, the formula for the slope is y1. So we might have y1 minus y0, or y2 minus y0, y1, whatever you want to call it. You have the difference in the y values divided by the difference in the x values, so x minus a. And you can see this is very familiar what we were doing in terms of velocity and things like that. Well, the general idea is we are going to allow x to go to a. So let me go under here. I want x to approach a. That means it's going to get closer and closer and closer. Let me sort of draw this a little thicker. It's going to get closer and closer. As it does so, it's going to trace out various different secant lines. Let me draw another one. See if I can get the hang of this. There's another one. Maybe another one. Let me just see if I can get another one in there. I'd use colors, but I've heard that some people have trouble with that, so I'm not going to bother with colors. There, I think I got it now. Well, what you're going to do is you're interested, as x goes to a, these points on the graph are going to get closer and closer and closer to a comma f of a, until finally in the limit you're going to get some graph, some line that will be tangent just in one point in that particular region. So the final line that you end up with, the one that touches just at that point locally, this line here is the tangent line, and I'm interested in the slope of that tangent line. That's the limit as x goes to a of f of x minus f of a all over x minus a. You may recognize this here as the instantaneous velocity. That's why these things are related to each other. Let me do an example. Compute the slope of the tangent line to x, well, let me call it f of x equals x squared. At any number a. Well, you'll remember we have m tan equals the limit as x goes to a, f of x minus f of a all over x minus a. F of x is equal to x squared. F of a is a squared. Of course, the numerator factors is x minus a times x plus a. Cancel out the x minus a's, and now I can replace my x with a. So this will equal 2a. Now you got to just tell me what x value you want the number at, and you can get the slope. For example, the slope of the tangent line at the point 1, comma 1 is m tan equals 2 times 1. You're replacing a with the x value, which equals 2. You might, let me just draw a real quick picture of this thing. We're doing y equals x squared, the basic parabola. At 1, let's just try to guesstimate here. It doesn't seem unreasonable that the slope of this tangent line could be 2. Doesn't seem unreasonable at all. How about the slope at, what is the slope of the tangent line at the point Let's try negative 1 comma 1. So in this case, a equals negative 1, and m tan equals 2 times negative 1 equals negative 2. And if I go on the other side of this graph to where I think negative 1 might be, you can see that it wouldn't be unreasonable for a tangent line to have a negative 2 slope there. You would see that the slope would be negative. So you can plug it any way you want, get the slope anywhere you want on the graph. Let me do another example. Compute the slope of the tangent line to f of x equals radical x at any number a. So same deal as before. M tan. Somehow, M tan though does not indicate where we're finding the derivative at, or the slope of the tangent line. M tan is the generic term. I'm not putting like parentheses a or anything like that. So this notation has some limitations. So anyways, the slope of the tangent line is x goes to a. The limit is x goes to a. F of x minus f of a all over x minus a. That equals the limit as x goes to a, square root of x minus the square root of a. And obviously, if this is to work, a would have to be a positive number. Or if a was 0, I would need to put a little plus after, because you can't approach 0 from the left with the square root over x minus a. Now, the most common way that people solve this is they multiply the numerator and denominator by the conjugate of the numerator. Kind of like rationalizing the numerator, if you will. I'm not a big fan of this. I would do it a slightly different way, but since this is so prevalent, and anywhere you look for this type of problem, you'll see people doing it in this fashion. So I figure I will do it this way as well. Now, when you do your FOIL method, radical x times radical x is just x. And then when you do the O and I part of FOIL, those things will cancel out until finally you get to radical a times radical a, and you get x minus a. And in the denominator, you get x minus a. It was already there. Don't forget your parentheses here, or you'll forget what you've been doing. Obviously, the x minus a's cancel out, and I'm left with the limit as x goes to a, 1 over the square root of x plus the square root of a. And it's at this point, assuming that a is not 0, of course, that you can see right here is another reason why I wouldn't want that. I'm going to replace x with a, and I get 1 over the square root of a plus the square root of a equals 1 over 2 times the square root of a. So just a quick reminder of what the square root looks like. I don't care about an exact thing here. It looks like this. So let's just say, what is m tan at a equal 4? So if this was 4, say, I'll have some sort of a tangent line that will touch just at that point. I hope I'm making that clear. I probably should use a better thing for it, but if I try sometimes, let's see if I can take that out of there. There we go. Let me try a better. Oh, it didn't take all of it, did it? Let's take away that stuff too. And try again a little better. Let me just try to get this one. Problem also. There we are. I think I got it. No, I didn't get it quite. But anyways, not quite horizontal, but it's not far away. M tan at a equals 4 equals 1 over 2 radical 4, which equals 1 over 4. So as you can see, that's not a very diagonal kind of a line. It's pretty flat. So my graph's a little bit off, but you get the idea, I hope. Now, different view. If you look at the limit, as x goes to a, f of x minus f of a all over x minus a, we have a preferred format that looks a little bit different than this. I'm going to let h equal x minus a. Thus, as x goes to a, h goes to 0. So the limit can be rewritten as the limit as x goes to a, f. What I'm going to do is this. I'm going to do f of x minus a plus a minus f of a. Remember, I didn't do anything. I added and subtracted an a inside those parentheses. And I got an x minus a down here. And this equals the limit as h goes to 0, f of h plus a minus f of a all over h. And this is the format that many times we'll prefer. This is the same thing. So let me rewrite the derivative at a. F prime of a equals the limit as h goes to 0. F of a plus h. For some reason we prefer a plus h instead of h plus a. Minus f of a all over h. This here is the derivative. Of f at a. This is really the big guy. Note that that is equal to f prime of a equals the limit as x goes to a, f of x minus f of a all over x minus a. So there's two different versions of it. I'm going to give you more than just these two. This second one to me is more of a velocity and tangent line type of a problem. This first type is more of a mathematical one that will have advantages in some computations. So let me redo f of x equals radical x using f prime of a equals the limit as h goes to 0, f of a plus h minus f of a all over h. You'll see we'll get the same answer as before. So I'll write the limit as h goes to 0. F of a plus h is the square root of a plus h minus the square root of a all over h. And the same game is going to be played. I can take this and multiply it by the square root of a plus h plus the square root of a all over square root of a plus h plus the square root of a. And just as before, this top part will turn out to be a difference of two squares. So I'll get a plus h minus a, and the bottom will be h times the square root of a plus h plus the square root of a. This equals the limit as h goes to 0. The a's cancel and I have just h. In the bottom I have h times the square root of a plus h plus the square root of a. So these h's cancel out. And then I'm left with, I can now plug in h equal to 0. I'll get the square root of a plus 0 plus the square root of a. And you can see that I'm going to get 1 over 2 times the square root of a, just as before. Okay, a lot of the times we would prefer to think of the derivative as a function. So when we had f of x equaled radical x, f prime of a equals 1 over 2 radical a. Well, if I simply forget about a and replace it with x, I can get a function in terms of x, 1 over 2 radical x. This here is preferable because now you think of the x as being a variable, and when you have a, you somehow think of a as being a static number that doesn't move. So when I had f of x equals x squared, f prime of a was 2a, but better yet, f prime of x equals 2x. In fact, in the formula for f prime of a, the limit as h goes to 0, f of a plus h minus f of a all over h, I can change this into a function of x by simply replacing the a with x. After all, a was allowed to be any number in the domain anyways. You still have the limit as h goes to 0. Now it looks like f of x plus h minus f of x over h. This one right here is the biggest one probably. This is the one we'll probably use most often. It has a lot of desirable algebraic traits that are very useful. So we'll call this the derivative function. Okay, let's do an example with it. I'll pick something, I won't be sheepish here. Let's do an example. Determine f prime of x when f of x equals 1 over x to the third. So the solution to that, I'll use this new formula that I have. Let me pull it down just a little bit. I can see it. I hope you can too. F prime of x equals the limit as h goes to 0, f of x plus h minus f of x all over h. Now let me go ahead and plug it into the formula, which is 1 over x cubed. Limit. As I said, this is not the easiest example to start with, but I've done plenty of other. You can go back and check x squared and radical x if you want to get more comfortable first. F of x plus h means that I plug x plus h in where I see x in the formula. So I'll have x plus h cubed minus f of x, 1 over x cubed, all of that divided by h. You may want to put parentheses because it's so big in there. Well, what I'm going to do in the numerator is get a common denominator. The easiest way to do that is this cross-multiplying scheme. You take this times this, come on, show, then this times this, and the denominator is x plus h cubed times x cubed. So I'll have x cubed minus x plus h cubed all over x plus h cubed times x cubed, and all of that is divided by h. Well, how do you work that thing? Well, it's probably easiest if you think of this h down here as being h over 1. This just destroys my students so many times. It's basic algebra. If you take a fraction, divide it by a fraction, you multiply by the reciprocal of the fraction. This is what you get. You get the limit as h goes to 0, x cubed minus x plus h cubed all over x plus h cubed, x cubed times h. So when you flip it, it becomes 1 over h and it multiplies to the denominator. Now what I'm going to do is factor the numerator. So I'm going to think of this. Remember, there's formulas for a cubed minus b cubed, and I'm going to use that one. I'll get x minus x plus h times x squared plus x times x plus h plus x plus h squared. All of this is over h. I'm sorry, x plus h cubed times x cubed times h. Now, I'm not going to simplify a lot except this first part here, this x minus x plus h, I can rewrite it as the limit. As h goes to 0, x minus x plus h just leaves me with a negative h. And I'm going to leave the other stuff alone. X squared plus x times x plus h plus x plus h squared. And all of that is over x plus h cubed times x cubed h. Let me fix that little cube down there if I can. Alright, now you can see the h's cancel. Don't forget there's a negative 1 there. It's at this stage I can replace all the h's with the number 0. So I still have that negative 1. X squared plus x times x plus 0 plus x plus 0 squared. All of that is divided by x plus 0 cubed times x cubed. And this equals negative 1 times, see, I had x squared, I had another x squared, and then I had a third x squared. And the denominator, I get x cubed times x cubed, like x to the 6th. So I get negative 3x squared over x to the 6th, which equals negative 3 over x to the 4th. So there's another notation. Even better yet, the physicists like this one. Instead of an h, so instead of h really is the amount that x and a vary from each other. Instead of h, so I'll put an OH, but instead of h, we can use delta x equal to h. This represents the change in the x values. That's very popular in the sciences, particularly physics. So in that case, then the derivative formula looks like this. Wherever you saw an h, change it to delta x. And there's another version of the derivative. So we have all of these different definitions, and each of them has their uses here and there. Like I said, the physicists like to use delta x. We'll use it plenty of times in this course. It's very useful to think that way. And then in a shorthand notation, then you'll often see this. F prime of x will equal the limit. Delta x goes to 0. But instead of having what I have here, the f of x plus delta x, etc., I'm going to put a delta y. It's like the change in y over the change in x. And this is a nice economical looking formula. And this will be defined by this formula, dy over dx. This is just a notation. So here is another notation for f prime of x. This notation is attributed to Leibniz, German mathematician and statesman who took an interest in helping to develop calculus, along with Newton. X squared plus x plus 1. So, as an example, compute f prime of x using the delta x definition. For f of x equals x squared plus x plus 1. So, f prime of x equals the limit as delta x goes to 0. This is no different than h being where delta x is. So, it's just another notation. Some are good for some things and some are better for other things. So you can see it's just replacing h with delta x. Let me go ahead and use the formula then. Delta x goes to 0. Everywhere I see an x in the formula for f, replace it with x plus delta x. So I have x plus delta x squared plus x plus delta x plus 1 minus x squared plus x plus 1. And that is all over delta x. It should go without saying that if I were just to plug in 0 for delta x, that I would get 0 over 0 and it wouldn't amount to much. But let me simplify a little bit if I can here. I have x plus delta x squared minus x squared. I'm putting the squares together. Plus x plus delta x minus, well, no, the 1 cancels actually, minus x. I don't need a parenthesis around that. All of that is over h. Most students choose to multiply out the x plus delta x squared, but just to remind you of some factoring, I noticed that this stuff right here is a difference of 2 squares, so I'm going to factor it like that. So I'll have x plus delta x minus x times x plus delta x plus x plus delta x. Notice that the x is canceled out over there. All this is over delta x. Just like h canceled in the previous problems, delta x is going to cancel in these problems. So the limit is delta x goes to 0. The x's cancel in the first piece, so I'll just have delta x times 2x plus delta x plus delta x all over delta x. In any of these derivative problems, if you don't have something to cancel out, you're not doing it right. So limit delta x goes to 0. I'm going to factor a delta x from the entire numerator. So what I'll have left is 2x plus delta x plus 1. If I take the delta x from delta x, I'm left with 1. Oh, look what I did. Gotta be careful about that. Delta x. Cancel these delta x's. Now I'm prepared to replace delta x with 0. So 2x plus 0, where the delta x was, plus 1. And the derivative is 2x plus 1. So, we have all sorts of interesting notations. We can write things like this. D parenthesis x squared plus x plus 1. This is like dy over dx can equal 2x plus 1. So that's another notation that we use. That's the Leibniz, sorry. I keep saying Leibniz, but it's Leibniz. Would use that kind of notation, or I'd simply say d, or he might say df over dx equals 2x plus 1. Or they might say dy over dx equals 2x plus 1. I mean, the possibilities are infinite. While we're here, let me do one last example before I wrap things up. Compute the equation of the tangent line to f of x equals x squared plus x plus 1 at x equals 4. what are the things you need in order to come up with the equation of a line? You need a point. So to get an equation of any line, you need a point and a slope. Let's start with the slope. M, call it M tan, is equal to f prime of 4, because 4 is the number we want. And remember, f prime of x is 2x plus 1, so if I replace x with 4, I get 2 times 4 plus 1, so that equals 9. So my slope is 9. Next I need the point. And usually the point, they call it like x, I think it's like x sub 0, y sub 0, depending on the book you have or something like that. But in our case, the x value was 4. I just need the y value. Well, f of 4 equals 4 squared plus 4 plus 1, which equals 21. So my point is that. So I've got my slope, and I've got my point, and therefore we can use the point-slope formula to get the equation of the line. I'm just going to remind you over here that the formula is given by this: y minus y0 equals m times x minus x0. So there you go. There's your equation of the line. If you're one of those people that insists that it be in slope-intercept form, sorry, not formula, but form, you can just rewrite it. I do not at all require that you rewrite it in the form, in this form. I don't care. Either one's, I'm fine with either one of these. So we'll call this quits. It's a monster lesson, I know. That's the end of our intro. The next few sections are going to go a lot faster because it's going to be mostly computational, less theory.